So apparently this and this should be in one part. They should connect to each other, and this and this and this should belong to a different part. So the way to change that is, so suppose you want to keep this as part 2 and you want to change this to part 2 also. So the way to do it is just click to select, then type part 1 to 1. Okay, now see, directly that was disconnected from this part 2 and connected to the part 1. So you want to move this to part 2. So part 2 negative to 1. Okay, now, so now they are matching size are connected in one part. So just refine again. Okay, it looks much healthier, right? Okay, so now the shift is setting down. Okay, good. And pretty healthy, right? Hash failed test will not fail in this case. Now you want to change it to anisotropic mode again, then press Ctrl R to refine. Yeah, good. It still behaves, that's good. Okay, continue to make continue to refine until this is settled down. Okay, good enough. And then the next step is to add hydrogen. Okay, so let's make sure the major model part is correct. Let's see the nitrogen are assigned. Let's see correctly. Yeah, generally looks fine. There are some extra electron density here, but not too outrageous. Yeah, good. Okay, what I'm going to do is Ctrl Q to bring up the Q peaks and Ctrl M to eliminate the maps. And again, this is one big Q peak there. We will worry about that later. Then we want to see the rest of the Q peaks. So electron density peaks. So there's only one huge peak there. What's the second peak? Q2. Let's select Q2. Okay, it's here. Then the next step is to add hydrogen. So again, adding hydrogen could be realized in two ways. Either you click add hydrogen here, and then we'll refine if you have this checked, or I prefer just each end. It's the same thing. Okay, now click refine. Yeah, refine a few more times. Refine. So mainly you can see this hydrogen are rotating, trying to find the most comfortable position, most low energy position. Okay, let's see what it is. Yes, still this oxygen is not settling down. See, whatever, let's see. Yeah, it's getting better. Okay. Yeah, it's rotating around, trying to find a comfortable position. So this, let's just increase this to 10. Click one more time. Okay, and we want to see if the hydrogen bonding is making sense. So just type H tab to bring up the hydrogen bonding. What's going on? Let's H tab, dash G. Okay, let's see. Yeah, most of them are making sense. Good, good. Okay, just type fuse to bring back to the asymmetric unit. Okay, let's continue to refine. And let's bring up the see, I already see one problem here, potential problem there. See, this proton is here and they have a Q peak in that position. Let's bring up the map again. Okay, and you can see that there are negative so electron hole here and cubic there. That means this proton should be here. So similarly, okay, that's the one I talked about just now, and similarly it's have another instance here. So proton position have a hole here, electron hole here, and possibly cubic right in the right position. If you check the distance, it's 0.875, just a perfect hydrogen in each bond there. And if you look carefully, this cubic actually lies on that plane, meaning this nitrogen is in the aromatic system. Similarly, for this case, this cubic lies on this plane. So the way to do it is either you just delete this one and name this as a proton, or what I recommend you to do is just choose this type mode fit. Okay, now you will see this special pointer, and you hold shift and click and hold on mouse and drag, and you let go the shift button and the left mouse button, and you just hold and drag the left mouse button to rotate the view and find another better view. Again, hold the shift, press the left mouse button, drag to make sure the overlap. Okay, try your best in this view direction. If it doesn't work, don't worry, you can always change different view direction and repeat this process. Okay, when it's there, let go the left mouse button and the shift button and rotate again. Okay, this is good. Not perfect, but it's good. It's already in that realm. It will automatically find its best, most comfortable position. Okay. Similarly, you want to do this to this proton. Okay. So again, of course, before that you have to exit this mode. So just press escape and click this one again. Mode fit. Hold the left mouse button, hold shift, drag, let that go and rotate the view. Do that again, hold shift, left mouse button, drag, rotate. Okay, let it go and repeat this process. I mean, it looks finicky in the first time, but if you practice many times, your hand can move much faster than your mind or your mouse. Okay, so then press escape to exit this mode. Then let's just refine again. Let's see 6.94. See what will change to. Okay, see, that means we are in the right direction. It drops the I1 and shifts. What's the shift? Let's see. Yeah, its shift is a different one, so it doesn't matter. And we want to repeat several times to see if anything will change. Okay, something is not correct. It's getting worse. Let's click this. Yeah, so that means, yeah, I know what's wrong. This is a nitrogen atom instead of the carbon. Let's check the model from the author. Okay, so basically we want to say this is a ligand they used, and also something wrong here, right? So I want to make sure it's check the model from the author, and this is the okay. Let's see. So basically, yes, see, these disordered atoms are actually nitrogen, and also, so this metal is connected to nitrogen, and also you notice here this nitrogen here is has no hydrogen bond because this is a sulfamide, something like that. So you can check the bond distance to make sure, but I believe it's double bond there, partial double bond nature there. So basically there are two mistakes in our current model. One is this, here is nitrogen atom, and here there's no proton. Okay, let's see. So that's a beauty of this, map. If you bring it up, you can see clearly there's an electron hole here. This hydrogen bond should not exist here. So just okay, so remove the map first. Click, delete. Similarly, I think the other way, yeah, this one also should remove this. Let's try and double check if that is an electron map, it shows a hole or not. It did not show as a whole, but I think it's this drawing level was too high. So, but anyway, we know this by chemistry knowledge. We know it's not there. So we remove that one, and also we want to make a correction here. Say, press Ctrl H to hide the hydrogen, and Ctrl Q to hide the Q peaks, and just choose these two to name them nitrogen. Then refine. Let's see the 6.88. Okay, 77, right direction. Good. Okay, cool. Finally settled down without any issue now. Okay. Let's see, Control R, Control H, Control Q, bring back everything, and then now we can see everything. Oh, okay. See that nitrogen should not have a proton there, of course, right? So basically, I want to see if that. Okay, so this nitrogen does not have a hydrogen, so we want to remove that hydrogen here and here. Here and here. This probably will not affect the IY value because it's very light. Yeah, it actually goes up a little bit. It doesn't matter because based on chemistry knowledge, you should not have hydrogen there. And also this is another good example that you should not only look at the IY value. Believe me, there are many ways to artificially lower the IY value, but it's not the correct way to do it. Okay, so I have to stress many times that especially for the new beginners. So now let's check this other part. I want to see this size looks better, matches better. So part 2 is pretty much 32%, and it's exactly the same occupancy because we tied them to part 2. So this is part 1. It's 1 minus that. 1 minus that 32 is 68%, and this should be the same occupancy, and the hydrogen are tied to the carbon. Let's see. Yeah, it's tied there. Good. So this is a correct chemistry model. And the next, the purpose I ignore the water here is I want to show you how to use squeeze or solvent mask to take care of the disordered solvent molecule. So if you know for sure, based on the synthesis procedure or the procedure to grow the crystals, you know that you only have water, and if you attempted to model this as water but failed because it's so diffuse, it does not settle down in a specific position. It just keep stretching that ellipsoid so large, just doesn't settle down. So the alternative to solve that problem is actually using the solvent mask or squeeze method called biplating. So this is a great opportunity for me to show that. That's why I actually did not try to model this at all. So the way to do it is here, very convenient. Right below the refine, you see this use solvent mask. Okay, so let me give you a brief explanation how to use this. So to use this, you first try to model the major part of the molecule pretty much ready other than this part. Then you can come here and check this use solvent mask. And you just click refine. Okay, and the program will calculate using a rolling ball model to calculate the void. So basically using, I think it's a 1.2 radius ball, rotate around to see where you can have that big void there. So calculate the void, then find the electron density in that void. And that's the volume, that's the electrons if they find there. So now they find 13 electrons. Okay, and since you know based on your chemistry knowledge that there's only water there, by the way, see that big peak are gone because it's covered by this solvent mask. Okay, so this max peak is removed. So 13 electrons, see how many waters it corresponds to. Okay, so you know there's two ways to do it. There's always more than one way to do it, to put it this way. So if you click the edit on the contents in the asymmetric unit, click edit, then you just put the type of solvent. You don't need to put the number, just put the identity of the solvent, like H2O. If it's methanol, you just put a methanol or the formula of the methanol and click OK. Then now you can see that the program automatically calculated it is close to 1 water, but it's only 10 electrons. Doesn't match that 13. So what you're going to do is come back here and change it to 1.3. So we just click OK. Now you can see, of course, hydrogens, H2O have like oxygen have 8 electrons, hydrogen have 1, so 2 hydrogens is 2 plus 8 is 10. 1.3 times 10 is 13. So now you purposefully play with this number to match up the electrons you found here. Of course, they match. Now they all turn green. That means it's good. Then just refine. Okay, now everything fall in shape. Good shape. See? Perfect. Refine again. And now it's time to check this button to let the program update the weight and take the weight into account during the refinement process. Okay, just click refine, watch this number will drop again at this number too. See? Magic. All of a sudden it dropped all deep green. Perfect. Other than here, let's just refine a little bit more. A little bit more. Okay, good. And check Ctrl M to bring up the map to see if any outstanding holes here. Yeah, there's big holes here. That means this proton is probably should not be there. So let me check the original model to see. This is a sulfamide and pyridine. See, look at this. Yeah, there's no proton on this nitrogen. Again, this is an aromatic ring, so it should not be a proton there. So I have to stress that this sample is not mine, so I don't know the chemistry formula or the expected structure. But in real life, when you have a sample, you know pretty well what you're looking for. So probably in the very beginning, you will know, oh, I do not have a proton here, so I should delete this proton in the very beginning. So this kind of mistake will not happen in real life. You will know in the beginning you should not have a proton there. So this is something you don't need to worry about. Okay, let's see what else. Yeah, so for the cubics near the heavy atoms, these are perfect normal. And for the cubics and for the positive density and electron holes near the heavy atoms, they are also perfectly normal because they are actually the consequence of the termination errors and absorption errors. So if you only find cubics near heavy atoms or electron density in the hole near heavy atoms, and you know for sure based on the chemistry knowledge, you know that atom type is correct, then you can, let it go, just as long as that cubic is not too big. Okay, so far looks pretty good to me. Okay, finally, check here. So you have to manually click here to add that molecule into this formula. Okay, and remember only click once, because if you click twice, it will add that formula again. Just to show you, if I click one more time, see, that's 2.6. If you click one more time, it's 3.9. So if you have end up here, the way to go back is to just click a refresh. That will come back here. So now you want to just click once. Okay. So that means it's included in the formula. And if you check here, it says solid mass was calculated, and this much of electrons were found in this volume, and this is consistent with the presence of 1 and 1.3 molecule water per asymmetric unit, blah blah blah. Of course, you can edit this a little bit, but this default format is fine. And this all green looks perfect, and there's no strange hydrogen bonding because you model the bonding as a writing model, so it is restrained to be within a reasonable bonding distance, and the occupancy is also in line with their master carbon atoms. And if you check with this major indicator, this is a perfect straight line, and you see two outliers here, and it's perfect normal to ignore a few of these outliers, and no referee will question this because this is not systematic. If you have a bunch of the outliers, or even the outliers are not random, they show underlying pattern, then you cannot just simply remove them or ignore them. You have to explain. It might be some kind of unaccounted training or even the space groups wrong, etc. But for just a couple of the outliers, just safely ignore it. No problem. It must be some kind of error, like beam stopping in the way, or the detector has a mini speck of dirt or whatever. You can, you don't need to explain at all. So now let's compare the previous result we downloaded from the CCDC database. Okay, so I believe I closed that window, so I'm going to reopen with Olex2. Anyway, let's see if I can show this. Yeah, okay. Let's see. Show this one here. Okay, so if you compare the side to side, this one is apparently tighter, right? This one, the right side one, the one we just go through the whole process of reproducing the refinement. This linearity is much better, much thinner, much tighter. This one is, it's very noisy, right? So that means we did a pretty good job, and we know we did a good job because the model now are clean. The model is better. Okay, so much for today. Hopefully I did not confuse you guys. And if you like this format, you like my this style, let me know, and I will try to make more of this series. try to find another data set and do the case study again. Last word, so if you want to prepare your own save file, just go here and choose ACTA and click refine. That will write a new copy of that zip file, which is now HTML file or REST file. All the necessary files are embedded correctly. That's a one advantage of the Olex2 program. Okay, so much for today. Hope you enjoyed, and if you do, please click the like button and let me know your thoughts on the comment area. Let me know if you like this case study series. Okay, have a nice day. Bye.